Okay, so what we can say is the main subject of the talk, or at least the starting point of the talk, is the connection between, well, it's what seems to be one of the main themes of the conference. So homotopy properties of p-completed classifying spaces versus local structure. Of G, or maybe local structure at the prime P. And one of the main examples of this has already been mentioned several times, namely the Martino-Pretty conjecture. So I won't restate that, but I would like to give one application of that result a little later on, because it's a very nice example of using homotopy theory to prove a purely group theoretic result. But what I'm mostly going to be concentrating on are questions about self-maps, comparing self-maps of these spaces with automorphisms of G. So, it's notation. When X is a space, I'll be writing out X for the set of homotopy classes of self-homotopy equivalences. So look at the monoid of all self-homotopy equivalences, modulo homotopy, and then, of course, that's a group. You can say it's the invertible elements in the set of all of homotopy classes of all maps, the monoid. And what's very elementary is that for G any discrete group, that out of BG, P complete, or the classifying space, is isomorphic to out of G. That's closely related to things that I think Benjamin said this morning. And so it, well, really comes from looking at all self-maps. So not just, oh, no, looking at pointed maps. So I'll write it this way. I haven't defined it, but take all homotopy equivalences, the preserved base point, modulo homotopies, the preserved base point. And you've got obvious maps back and forth with aught of G. In one direction, you take pi 1. The other direction, you take the classifying space as a functor, and it's well known that this is an isomorphism. And then from there, one checks that it factors through an isomorphism between unpointed self-homotopy equivalences and the outer automorphism group. And of course, that's what originally motivated using this notation. And so But I want to talk about, one of the things I want to talk about is identifying this group. Okay, so now on the other side, the p-local structure of G, well, again, I'm not going to repeat the definition of the fusion system for G. But I think I will repeat the definition of the centric linking system for G, since that was defined once fairly quickly. And so for the centric linking system, well, first of all, we say that is p-centric in G if different ways of defining it, but the one property that I'll be using here is that the centralizer of P splits as the product of the center of P with a group of prime power order. And now, the linking system is the category whose objects are the p-centric subgroups. And where the morphisms well, take the transporter set of all G in G such that G conjugates P into Q modulo CG prime of P. And as always already been noted, we can the homomorphisms from P to Q in F can be identified with a set of morphisms in L from P to Q modulo a free action of the center of P. And that just comes by comparing this group C prime, CG prime of P with the full centralizer. And the first hint as the connection between this category, the linking category, and homotopy was the theorem with Brodo and Levy that take the geometric realization of the linking category, P complete, then that's equivalent, homotopy equivalent to BGP completed. Yeah. So now to look at automorphisms. So automorphisms of the fusion system have already been defined, essentially, maybe not formally. But so keeping the same situation where S is a C-left subgroup of G, and in fact everything I'm going to say also works for abstract fusion and linking systems, but to keep it simple, I'll stick to this case. So I'll call that F. So aut of F is the set of alpha in aut of S, automorphisms of S that preserve the fusion. In other words, that alpha extends to alpha hat an automorphism of the category F, where this is simply the automorphism that on objects sends P to alpha of P, and on morphisms sends phi, say from P to Q, to alpha phi alpha inverse, composing from right to left. Okay, so it extends in the obvious, unique possible way to an automorphism of the category F. And then the outer automorphism group turns out to be most natural to define it as, well, it's always the question what to divide out by, and in this case, the F divide out by the F automorphisms of S. And then, okay, I'll leave it at that for the time being. Well, maybe I'll just say that there is a natural map from out of G that I'll define in a little while. From automorphisms of the group to automorphisms of its fusion system, and which is one of the things that I want to study. So I'll define that shortly. But first, go to the linking systems, because a priori you might think that this out of F is the most natural group for studying automorphisms of the fusion, but it turns out not to be the case. And the reason can be seen in the following example. So I'm looking at the case where G is alternating group on 6 letters, A6, and we've got 2 extensions. Sigma 6 and A6 cross group of order 2, so are both semi-direct products with group of order 2, and obviously very different as groups, but you don't see this difference as an element of the fusion system, as an automorphism of the fusion system. And the way to see that is, well, you've got A6, and now aught of the fusion system S of A6, where let me take out. So I'll take S to be the subgroup. I'll write it this way. Going to write 1, 2, 3, 3, 4, 5, 6, and 1, 3, 2, 4, intersected with A6. So what I've got in here is a CELOF2 subgroup of S6, of the symmetric group, and then I'm intersecting with A6. And so that's easily seen to be dihedral of order 8. But what's in here is D8 cross C2, because, yeah. And now, but this is represented by conjugation by 5, 6. 5, 6 is obviously an odd permutation, and conjugation by that is a generator. What I really want, well, no, it's not a generator, because out of A6, I'm forgetting, has order 4, but it's the generator we're interested in, the outer automorphism that generates S6. But when you move in here, this element, conjugation by this element, centralizes S. And so this goes to the identity in S as an automorphism of S, and hence as an automorphism of the fusion system. So, in other words, the fusion system of sigma 6 and of A6 cross C2 are semi-direct products, are both well, with the trivial automorphism of the fusion system of A6. But they're not the same, they're not isomorphic fusion systems. And so what this is saying is that just looking at automorphism of the fusion system isn't good enough if you want to be able to talk about, use them to understand extensions. And so just, this is all motivation. One part of the motivation for looking at automorphisms of the linking system. Okay. Yeah. I'm not sure I can answer that standing here. I mean, I can talk with you afterwards, but let me just say that for G equal A6, out of F has order 2, and out of L has order 4. Okay. Yeah. Yeah. And actually constructing it, well, first I have to define the automorphism group of L. But afterwards, I don't think I really have time even to here to do that. So, well, we have now okay, I've erased it now, the definition of the linking system, but G, well, got certain elements, certain automorphisms or morphisms for each object. Namely, we've got an inclusion, can be thought of as the class of 1 as an as a morphism from P to S, because the class of 1 as an element of the transporter set from P to S. And we've got a homomorphism, a monomorphism, delta sub P from P to aught sub L of P that sends element G to the class of G, since this thing is just normalizer in G of P mod CG prime of P. That's really equal. And now, so aught of L, the automorphisms of the linking system L are defined to be, it's the group of all automorphisms of the category L that preserve these structures. So set of all alpha, or let's call it beta, automorphisms of the category L, such that beta sends inclusion of P to the inclusion of beta of P, and beta sends the image of this to delta beta of P of beta of P for all P. So preserves both of these structures. And, as usual, it's an outer automorphism group that turns out to be natural, divide out by conjugation by elements in aught sub L of S. Which means that if you've got a morphism in L, conjugating it by gamma really means conjugating it by appropriate restrictions of gamma. Okay, so now we've got homomorphisms. And we've been calling this kappa bar composite, where, well, first of all, to make this more obvious what these maps are, let me just note that out of G can be identified with those elements in the automorphism group that send the CELO to itself modulo those elements in the inner automorphism that send the CELO to itself. Okay, so that's straightforward. It's just a matter of checking that every class in out of G contains an automorphism that sends S to itself, which is some version of the Frattini argument. So, for example, kappa bar of G is basically just restriction to S. So it sends alpha to alpha restriction to S. It's not hard to see that that's well defined. Kappa sub G is fairly clear because I'll be lazy and just write easy. But what that means is that if you just look at the definition of L, it's obvious how if you've got an automorphism of G that sends S to itself, then it clearly induces an automorphism of the linking system in an obvious way. And then mu sub G is again a form of restriction map. So basically an element here is a class of automorphisms of S, and you can identify inside of here you've got delta of S, a certain subgroup, as a subgroup of aught sub L of S. And so if you've got an automorphism of L, you restrict it to, it's going to send this group to itself, it's going to send this to itself, and that's an automorphism. Okay. So in general, these are neither injective nor surjective. They can be anything. But one can say a lot more about mu sub G, the theorem, which is a special case of the result that's been mentioned already in other versions. So do the Chermak and then Glauberman-Lind says that mu sub G is always surjective. It's injective if P is odd, and if P is equal to 2, then kernel of mu sub G, well, what's easy is that it's an abelian 2 group, and by a recent result that, are you confident enough for me to announce it or tell? Yeah, okay. By it's elementary abelian. Okay. So in this case, one can say a lot, and these two are similar, but there are enough examples. I've already given one example, or well, where I stated that it's not an isomorphism. There's, one other result that I wanted to mention before continuing. Namely, result of mine with Ron and Carlos that for all P, we have that out of BGP completed is isomorphic to out of the linking system. So this is another indication that the outer automorphism group of the linking system is really a more natural group to look at than the outer automorphism group of the fusion system, at least when they're not isomorphic. Not sure I follow the question. You mean, can I describe where those maps come from? I can't remember whether, to what extent we did that or not. If we looked at that, it would have been in the last section of BL01 where we did look at A6, automorphisms of A6 and other groups of the PSL2Q type, not the prime 2, but I don't remember how precisely we did that exactly. And actually maybe, I think some of that was done by Carlos and Ron in their paper before we started collaborating, the three of us. Okay. So now to some more concrete applications, where first I said I wanted to give an application of the Martino-Pretty conjecture, or at least one direction, one of the implications there, which is the so-called easy, or at least it used to be considered the easy direction since it didn't involve the classification. By now, it might be the hard direction. But anyhow, theorem mine with Carlos Broto and Jesper Müller is that if you've got G, and let me make sure I get all of the conditions connected. Simple group scheme. Over the integers. I'll say a little more about that shortly. P is a prime. Q and Q prime are prime powers. Such that, which are both prime to P. And then, well, if Q and Q prime generate the same closed subgroup of the p-adic units. So take the subgroup they generate, take their closures in the p-adic topology. Those two are equal. Then that implies that G Q and G of Q prime have the same fusion. So I'll say this. I meant to define the notation before, where G prime means that Fs of G is isomorphic as a fusion system to Fs prime of G prime, meaning isomorphic as a fusion system, meaning via an isomorphism of CLUF subgroups, induced by an isomorphism of CLUF subgroups. Okay. And let me just say the proof by showing that B G of Q, P completed, is homotope equivalent to B G of Q prime, P completed. And it's a result for which, as far as I know, there's no purely algebraic proof known, unless somebody's come up with one recently. And the only proof is this one that involves various homotopy theoretical techniques and including the Sullivan conjecture. The main problem with this is that Q and Q prime could be primes of different powers of different primes, so that it's hard algebraically, so there might not be any homomorphisms connecting them. Yeah? Oh, sorry, that means G, yeah, I was going to say a little more about that. So G, for example, means, I mean, think of a group scheme as a functor from commutative rings to groups. So G can be SLN, PSLN, and then SP2N, E6, so forth. And this means evaluated on the field of that order. Yeah, so G of Q means G of field of order Q. Yeah. And I'll come back to that towards the end, if there's time, with some examples. But as you see, there are lots of examples of distinct groups with different defining characteristics that have the same fusion, according to this. So now, back to automorphisms of the groups. And here, one of the ideas, central ideas that comes up is tameness. So say that F is tame. This could be any fusion system over G. If there exists finite group G star such that, well, S CeLO G star, F, the given fusion system, is equal to the fusion system of G star, and this map kappa sub G star out of G star is split surjective. And note, of course, that this is isomorphic to out the linking system of G, since we're assuming that the fusion systems are isomorphic. And so by this theorem that's been talked about several times, if the fusion systems are isomorphic, then the linking systems are isomorphic. Okay, so this is split surjective. Not sure I'll have time at the end to give an example of a theorem that uses this. But let me just say at this point that it comes up when looking at extensions, trying to work out extensions of F or of L. Because we're in the situation where, just saying this very roughly, so say this comes from an extension of L. Say extension of L by a group K, finite group K. I won't say exactly what that means. Extension of L has the obvious meaning that it's a larger linking system which contains this as a normal subsystem. Got kappa. And we want to be able to lift this in order to realize, because what we want to do is realize the extension by an extension of G star. And, well, of course, there's a lot more to extensions than just figuring out the outer action, but at least that's the first step. If you want to get an extension, if you want to construct an extension of G star by K, then you'd better start off by constructing a homomorphism from K to out of G star. And this property of being split surjective is equivalent to saying that you can always do that. So now I want to focus on the case of simple groups. And so the first theorem is easily stated. F S of G for some, let me say, known simple group. Then F is tame. Okay, sorry, there's one thing I forgot to write here. Definition, end of the definition I want to come back to afterwards. We'll say that F is tamely realized by G star. Tamely realized by any group with the same fusion, with F as fusion system for which this kappa is split surjective. So in this case, F is tame. It might not be tamely realized by G, but it's always tamely realized by some group. So the second theorem is a lot more precise, but also somewhat more limited. So fix P a prime, G finite simple group, S a Celoff subgroup, and assume that S is non-abelian. And I'll also assume that G is one of the following. Either G is a n for n congruent to 0 or 1 mod p, so for example, this is no restriction obviously when p equals 2, or G is a sporadic group or G, let's write it this way, G is a finite group of Lie type and characteristic P. And the same characteristic. And then the conclusion is the kappa sub G is an isomorphism with just 4 exceptions. I'll write as pairs G and P. And so this is first A7, 2. SL3 of 2 at 2. Mathieu 11 at 2. And then Held's group at 3. Okay. So it's very surprising that, that there are so few exceptions. And I don't know that there are a lot more exceptions if we, well, obviously you've got to have some restriction. on the Celoff subgroups, because if you allow the trivial group, then you'll always get the trivial. I mean, out of L will always be trivial. But I think you can, I mean, it's true in many more cases, I think, if you allow non-cyclic abelian groups as Celoff subgroups for these groups. Okay, so what's been left out here? Well, you've got this restriction, which occurs only because without this condition, if n is not 0 or 1 mod p, then the fusion system of the alternating group A sub n is isomorphic to the fusion system of sigma sub n, of the symmetric group. And so you're going to definitely end up with a different automorphism group. And then the other big gap, big thing that's missing here are the groups of Lie type in cross characteristic. And so that's what I want to finish with, just a few examples. Because, to put it very briefly, when G's of Lie type in characteristic different from P, then, well, this kappa sub G might be neither surjective nor injective, need not have any nice properties, but one can always replace G by another group of Lie type, maybe not in the same characteristic, in characteristic prime to P, with the same fusion system where this is true, where it is split surjective. So simplest example is the case, let's take Q 16, and I'll take Q prime to be 9, and G to be PSL2Q, G prime, or well, guess I be consistent with earlier notation, G star is PSL2 And now we know outer automorphism of G is well, it's C2 cross C sub M, where M is the largest power of which this is a prime. So where Q naught to the M, Q naught prime. So this is the diagonal automorphism, and then these are the field automorphisms. And okay, so automorphism group of the group is well known due to, well, the general result due to Steinberg. This case, probably back a century or more. And then And now, so obviously, and G, we're taking the prime 2, G's equivalent to G star for all Q. This doesn't follow from the result I wrote down earlier, because, well, note that, well, in all cases, the subgroup generated by plus or minus Q, closed subgroup generated by plus minus Q, is equal to the closed subgroup generated by, for all such Q, for all Q under these conditions. And it turns out that for PSL2, in this particular case, it's enough that they generate the same thing up to sign. Okay, so all of these generate, for example, all of them have a CLUF2 subgroup of order 8, dihedral of order 8, and so on. And so out of G, in each case, is C2 cross C2, and kappa sub G star is an isomorphism. Because we get, I mean, the special case, when Q equals Q star, when Q equals 9, then M equals 2, obviously. And so we have the field automorphism of order 2. Maybe, yes, I was forgetting this. Let me note that A6 is isomorphic to PSL2 9. So that this comes back to your question about, so the automorphisms of L actually do come from automorphisms of the groove. It's just that one of those automorphisms disappears when you look in the fusion system. And okay, and so that's all. No, as far as I can remember, you can always do that. Now, maybe not always exactly the same type. In other words, sometimes there are questions of switching between PSLN and PSUN, or maybe there are a couple other things like that. But I mean, in our paper, I mean, to prove that they're all tame, we have to explicitly work out exactly what gets replaced by what in all cases. And so they always get replaced by another group of Lie type in characteristic different from P, maybe different characteristic, maybe even a different type, different group scheme. But yeah. Not sure. Did that answer your question? Yeah.
So your map can be that. So out of P, that's the same as out of EP.
Yes.
And out of L is the same as out of BTP completed.
Yes. Yes.
And so if you have a self-map of BG, then you can take P completion of that map.
It's the same thing.
And that's coincides with cavity.
Yeah. I can't remember. No, I hope we wrote that down explicitly somewhere now. But, yeah.
This lifting argument says if you have a tame fusion system, not tame one, then you could construct bad examples not realizable.
Yes. That was part of our, the idea of tameness came up first in a paper of mine with Caspar-Andersen and Joana-Ventura, and that was one of the things we showed. And one of our motivations for it, for talking about tameness, was we were trying to detect exotic examples and showed that, there's a certain class of fusion systems that we called reduced. Everything reduces to a reduced fusion system. If it reduces to a tame fusion system, then it has to be tame. And if you've got a fusion system that's not tame, then there's something exotic that reduces to it. Yeah, so that was the original motivation. Now the problem is, what I should note, that we still do not have any examples of a realizable fusion system that's not tame, that we know is not tame. Yeah, very much like an example. We assumed at the beginning it should be easy to find examples, but they seem to be well hidden. No, they're all tame. Theorem 1, yeah, all fusion systems of all simple groups are tame. But for example, in the case of A7, it's tamely realized by A6. A7 and A6 have the same fusion. The difference is that A6 has outer automorphism group of order 4, while A7 has order 2 only.
Exception means it's not isomorphism, but it's still surjective.
Well, in the case of A7, it's injective and not surjective. In the case of SL32, I guess it's not surjective, but SL32 has the same fusion as A6 also. So it's tamely realized by A6. In the case of M11, I'd have to think back, but it's L3 of something, PSL3 of 3, yeah, it realizes it. Yeah, okay. And then Held's group, I forget. But I think in Held's group, I think the CELO is extra special, isn't it, of order 3 cubed, and so I think there are a few other groups with the same fusion.